Okay, so we previously discussed the cylinder equations and microscopic derivation of the same. We also discussed an example, which is a one single bosonic oscillator coupled to many such oscillators, and we did some computations from the GKSL equation, which we compared with the quantum Lagrange equation computations, which we basically compared at the level of steady state properties. So now coming to, let's focus on the second part of this lectures, which are open quantum field theories. And here, while studying this formalism, what we will see is that what is important as well is that in certain cases, for example, in the cases that we are going to discuss, it is problematic to use the Feynman's I epsilon prescription, and as well as the time ordering thing breaks down in certain cases. And which are those cases? Basically, some of those examples are non-equilibrium statement. So we also know that when we were studying this evolution of a system density matrix, that was out of equilibrium, and when we take t going to infinity limit, it becomes a thermally density matrix that is in thermal equilibrium in the same temperature as the bath. We saw this, but in general, it will also be a non-equilibrium situation. And some examples of this are plasma physics, cosmology, and X-ray, laser. These are the situations where time modeling, certain out of time order. So what I mean is that we have to consider out of time order correlators as well while talking about studying the evolution of these density matrices. Basically, what I mean is that if you do not have, the main point is that you do not have the in vacuum and the out vacuum to be the same. Or rather, yeah, and in that case, basically, one avoids talking about the out vacuum and basically forward evolves with the in vacuum as well as backward evolves and gets to the same thing. So when we see this formulation, but we will see that the terms that appear in a, let's say, Green's function, some of them will be time ordered, but some of them can also be, because we are having a backward time evolution as well. In that backward time evolution, some of the terms will be anti-time ordered, and there will be correlators which are not time ordered at all. So there is no time ordering involved in such correlators. Not the only contributors. Yes. 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 And these cases usually appear, which are also coming from this case, which is that one needs to deal with evolution of density matrices. In our usual path integral formulation, we usually study states and so on, but states and fields. But in these cases, one needs to deal with evolution of density matrices, which again along the evolution can turn from a, say, as we assumed in our previous study that initial density matrix that we will have there, the system and the environment will be decoupled. But as time moves on, my density matrix can be density matrix for mixed state. So let's start our discussion by discussing where this time modeling or how this time modeling appeared in usual time evolution of operators in interaction picture, and we will see where we need to change things to basically what I mentioned that. So in these cases, out vacuum is not same as the in vacuum. So we will see that to avoid this problem, we will just deal with in vacuum, which will be the way which is called the finger gauge for problem. So to begin with, let's say you have again free Hamiltonian plus an interacting part of the Hamiltonian. And if we compare the interaction and Heisenberg pictures, that this UP, so this is the Heisenberg picture, and this is the interaction picture operator. So this UP will be for a general time-dependent Hamiltonian, say, these are time-dependent, then it will be, even in case of time-independent, most general case should look like this. Which are this. And let's say so the vacuums for this free theory we denote it by 0, and the vacuum of this interacting theory we denote it by 2. So if we want to compute 2-point correlation function in the interacting theory vacuum, turns out that, for example, we use all of these things here with T1 and then T2, and then we should also remember that U dagger T1 comma 0. Now remember this will also hold that U dagger T1 T2 in general is equal to U. But there is a just difference of minus sign. Now these two give me a basically, so this will be U of 0 comma t, and the whole thing will be 1 comma t.
So the in vacuum is basically starting a closed system and vacuum is a closed system. In vacuum or vacuum.
Yeah.
How is it happening?
The vacuum. Sorry.
I mean, how is the process happening? So
Because this there is mixed entanglement going on between this this density matrix evolution that we are looking at. It might turn from pure to mixed density matrix along the way. So that in the most general case that we deal with the out vacuum in T going to infinity plus infinity will not be the, of course will keep getting mixed and mixed. So even if you go to time going to infinity, you will not get a zero vacuum where it was not entangled, the total density matrix that you had. Because in the initial state your density matrix was decoupled. But as you keep evolving with time, there is this interacting part in the Hamiltonian that will decouple the system density matrix to this environmental density matrix, and it will keep making it more and more mixed. It will not make it pure anytime. So here my final solution is this. So for this vacuum, omega, say the ground state energy is this. For the full Hamiltonian, whereas for the free Hamiltonian, on the free vacuum, it is defined as this. For the free Hamiltonian. Now, let's say what we want to do is we want to write this things. Of course, we can only replace this interacting theory vacuum or the more general H theory vacuum in terms of the free vacuum only in interaction picture. We cannot do it in Schrodinger or Heisenberg picture. So let's try to write this omega in terms of 0. Or rather, yeah, omega will try to do it. So basically what we do, let's say fish. This is just for now something we don't care much about it. This is just a constant thing where we start the evolution from it can be 0 in 0, let's keep it as t0. If we act some 0, the free theory vacuum, let's consider from t0 going to 0, so to do that. You can write as sum over this thing, the same, the excited state of the interacting theory. Which we excite quite easily. So these are the excited states. And if we just use the eigenvalues, because all of these will give certain eigenvalues here, this will give me E0 and this will give me EA. Now there is a trick to move forward, which is basically taking. So we want to study eventually what happens in the. So here still we are talking about a usual case where we would see the in vacuum is the out vacuum. The in vacuum in fact is the out vacuum. T naught, I just thought the starting point is, let's say, consider T not equals to 0. So if I take this T going to infinity limit, ideally I should take. So what happens is that with the T going to infinity limit, these things, there are a couple of ways to understand this. Firstly, these are higher energy levels. This will contribute less and less. In the T going to infinity limit, this will become very rapidly oscillating and average out to 0. Another way of mathematical way of looking at it is if I consider this I epsilon prescription where I take t, where I consider a very small imaginary part in my line coordinate. Then what happens that the only so these will become what I n, of course the infinity part you can treat this as a phase. The other part will be just minus epsilon epsilon into En. So this will contribute very less, and the only contribution will come from this term. So in the t going to infinity minus I epsilon, you can in fact just write the first term from this expansion.
Don't you also have a equals infinity in the first expression too?
Sorry?
T tends to infinity minus I epsilon. Don't you have the
Yeah. We have that, but this is the lowest energy level. So among all of the possible things, this will contribute the because t going to infinity is this will become very small. So they are the only among all possible things the smallest contribution we will do, which comes from the vacuum. And then we can basically from this expression write omega. Inverse of this. Now what we can also do is remember this h acting on 0 acting on 0 was given me 0. So e to the power anything like plus I 0 t acting on 0 will give me just the vacuum state. So we can replace this by this. Everything else remains the same, it's fine. Now we can simply make this as flat. Use those two things, and basically we will be able to write it in terms of the interacting entropy. And these two things eventually give me this. Actually, if I again make this T0 part, which I omitted earlier. This is again written in interaction picture. Now if I use this expression that I have, firstly if I have a limit, then I will have this term, then I will have a u dagger, or u, so you just have to change it. Now if we use this expression over here, then what we get is the final thing. here basically what I will get is from this expression I will get a ut comma 0 here, and then the next expression I have is u dagger t1 comma 0, which we can write as u0 comma t1. So multiplying this with the earlier thing, which will give us this, we will get this thing. Now, if we look at this part and carefully do the time ordering, carefully understand time ordering in each of those terms, because these terms are already sort of time ordered from my definition of u. So, this part becomes 0 time order. On the other hand, if I again use this part of the thing and compute something like a inner product of these two vacuums, we find that it is nothing but what we have in the first one. This thing I can replace here, and this is actually nothing but so here what? I replace this part here, and the final expression will be something like time order, OI T1, OI T2, UT comma minus T, sandwiched over this free vacuum states, divided by just this thing, 0 UT comma minus T, 0. So and in my scattering picture, I know that if I take this capital T's to infinity, then I get the scattering operator, which is the u infinity comma minus infinity operator. This becomes this. In these cases, what happens is out vacuum same as the in vacuum up to a phase, but this is what will not hold in case of the open systems, or rather the cases that where we are going to apply Hübner-Geldish. the density matrix or the state becomes mixed along the way, along the evolution, and so this will not hold in general. And this again means that our vacuum is not close to the vacuum when it's not true upward phase. So how do we deal with such situations? Is basically by avoiding the discussion of out vacuum, and this formalism is known as this finger pinch formalism that I am going to discuss now. Are there any questions to this point? Questions or confusions? Yeah. Yes. It is the interaction is turned on for very small time. Very slowly the interaction is turned on and goes off. The interaction stays for the whole time period where we are studying the evolution. We cannot really approximate this final state by the same vacuum as the initial. Okay, so let's start by writing down the transition amplitude of a crystal from emit state to emit state. In the path integral formulation, how do we write this? Is this part. Basically, what we will do is take something like a phi n to the power is or to the power ih t phi n, and that expression is we write in terms of the position and let's say in the position states, then what we get is this position wave function. So you can think of this. Let's say my phi n is we define that x2 t2 and phi n is x1 t1. But this is a function. So we also have a dx2 and dx1. So in path integral, we start from this, we go from, let's say, this time steps, we start from, let's say, this part. This is my t direction. This is t1, this is t2. Starting from x1 and ending at x2. I have many dx's, small time steps and small position steps in which I have divided this whole integral. So I have kept here the dx2 and dx1 part where I will have to use the boundary conditions later on. But the rest of the things, so we have included in this. And this is basically this part. This is what we write it as kx2 t2 x1. And if we start from this probability transition amplitude and write the probability, basically we'll have to take two such things. Sorry? Yeah, so IM and these are basically yeah. introduce a primed index because we'll have to take two such things A and M star, and for those we'll have to find parameters of this prime. So here I have dx and dx prime. Sorry? PNM is the probability. Transition amplitudes are like just psi things, right? Then probability you have to take psi star model. And if we basically, the idea is if we sum of the down states, which are these phi n's, we will get rho n, which are density matrix elements. And in this expression, the effective, this part we call the effective kernel. Which is basically this thing divided to this part, this way. This we are writing is nothing but a 2. So 2 bar 52 minus h prime. Sorry?
So what does it mean to sum over the outstates? I integrate PNM against.
Yeah, so PNM against the n states. So basically here I will take a sum over the n states as well, summation over n. If I perform that integration inside this, if I perform that integration only for sum over n's for all possible phi n's that are in the out state, then from this probabilities we will get the density matrix elements corresponding to the in state that I have for arbitrary times.
So this is the formula I'm asking. So the formula for ONN is integral of PNM against let's say phi n. I'm not understanding what the
Oh,
formula for ONN is.
yeah, let me go down. So let's say if I have a psi of phi 1, which is something like d phi 1. By this I am still writing in terms of the fields. Then my density matrix look like something of this kind. And this part you just, here I am writing 5, 5, 9, but here you can think of this as this in terms of this dx kind of thing. But basically what I am trying to say is that I will integrate over this x2 spaces to get the this integration I will do. But dx1 prime integration will still stay. So even in the dx prime as well, I will only perform the x2 integrations that are there. And whatever we get will be the, so inside the BNM we will be somehow write it as something like ONM into this IN star, IN, and all of the things that I am integrating here. After integration, whatever is left is well. The other thing is, if I sum over this thing, I should get the probability to be 1.
So the motivation was to construct path integral representation of the density.
Yes, that's so. This is how we can, after doing one integration, I will write the expression of the density matrix as well. So what we want to do, because where the information we will have is, let's say the boundary conditions that I will put is, I have a initial density matrix which I will put as the boundary condition at my x1 time scale, and x2 and x2 prime I will identify basically taking this trace where I say trace of this. So to define a density matrix, also you have to define a trace over the other degrees of freedom. It's in the x2 part. If we take those traces, then that trace I have to take here through this integration. And this part will look like, so this you can think of, for example, like I'm taking only sum over n, so it is like tracing over the out states, and that probability, for example, the probabilities in a density matrix that add up to 1. So that is what I am putting it as 1 here, and so what I get here is that I take the sum over n. This part will give me delta x2 minus delta x2 prime. This is just by using the field equations at any point. And so one of these will go out. We can write this as just one thing. So this one will have one dx2 or either dx2 or dx2. Basically, that means that we will be able to, if we take this sum, we will be able to identify this x2 as x2 prime. Summing over the final state means at the kernel that we find here, x2, x2 prime, x1 prime, x1. You can put this delta function into use. And specify final degrees of freedom, that is x2 at t2. So this now the kernel that we will have is for the Schwinger-Keldysh kernel. We'll have just one x2 instead of x2 x2 prime. Here we have boundary condition where, for example, I mentioned I can perform this integration and get the initial density matrix, which we will call this rho x1 x1 prime, which will be only a function of x1 x1 prime, and at one thing is just we will identify here. So this is also called the Schwinger-Keldysh path integral. And what this means is that here we have T1, so what we do here is that firstly forward evolve. Evolution of this rho x1 x1 prime, let's say, from t1 to t2, and then we backward evolve. From t2 to t1. So this relative minus sign that we have here, you can think of this as the result of my backward evolution that I am doing from T2 to T1, so that and that in the middle phase basically we treat this as 3. The second 2 would be identifying the 2 branches. At T2, which is basically x2 plus x2 prime.
How are you getting this lower limit of low?
Sorry?
Lower limit of this integral.
If you, from this expression, if you just perform the integration of the final fields that are phi n x2 integration, if you do, then whatever is left is your density matrix, initial density matrix at x1, because we are integrating over the x2 fields. But when you have is the initial density matrix that you start over. That expression will act as your boundary condition at the initial time, initial density.
What is meant by this PNN equal to 1?
PNN equals to 1, basically you can again think of this as that let's say you had this rho equals to so if you take this sum then they will be bounded.
Actually, this aim, what happens to the aim?
Main part is what yeah, that is you started from a full state. When you summing over n here means, I think as far as I understand, is you are computing whatever you are talking about is the probabilities that are in your density matrix in terms of the classical probability mixtures that you have. Since you haven't made the n thing, that will also probably not sure, but that will probably also be 1. But that is a different probability from this. This is the probability from mth to nth level. Right? So,
Yeah, but
yeah. So mth to nth level, if you sum over all the possibilities from m, this is basically, you can treat this as jumping from
I think it is keeping the m fixed.
yeah, that is what I'm saying. So if you keep the m fixed, then all the possible energy levels that you have, the total probability of jumping to all those energy levels should be 1. That is equivalent to sort of that expression. Then I don't think at the same time whether you can sum over n and m both. Or what does that mean? I mean, you have all possible energy states and all possible energy states that it is jumping to. That probability should also give me 1, but I'm not sure how to deal with it in this picture. Something I have to fix just. I mean, we are just talking about transition.
Then there will be another delta function with that x.
Yeah, so basically everything will go out and still I think you should get 1. But here it is for the fixed case, but I don't think, yeah, so I don't think you have the same expression you had in sum as well. I'm not sure what happens if I take this out as well. Then at least here. Yeah.
For this, I think we need to start from this. I mean, here we could have started with this expression, and then if you want to compute the matrix elements of this, so and then nobody wanted to compute the way
Yeah.
matrix elements.
Yeah.
So then you will insert states from both sides, and then Kamble just work out the particular representation of this waveform.
Exactly. This is usually how this Schwinger-Kelvich path integral is defined. But what is the reason of doing it this way? That I'm not sure. But
It looks like that is
yeah.
But this is I was saying that yeah. So this is a natural thing seems like it's like that. You start from the definition of the density matrix, which is what you want to compare, and then you want to compute matrix elements.
Yes.
So you sandwich this with states space and then you use overlaps n of n with some n prime with n and some I n with n.
Yeah.
And then you basically do those overlaps with the path integral.
Yeah. I think, yeah, that is also another way. So, basically, this is one way to, the main reason of doing this was, I think, again, that is related to what, we can also do it the way that you said, but the main reason of fixing, let's say, one thing and the final state, for example, we can start from a particular state. Somewhere we have to start, but we don't know in which level it is going to jump. So, let's say I know the initial state, that is for which I am putting the boundary conditions as well. I always know what my initial state is, where the state was decoupled, and what is my initial state density matrix. So I have information about the phi n's most of the times, but I don't have enough information about the phi n's ever. So it can be the possibilities or the probabilities that I want to consider. I have to, in general, consider all it jumping to all possible n values. Huh? This is just saying if you have a particle at mth energy level, you can jump to all possible energy levels, and if you compute if you keep the mth energy level that you know, which is the initial state. Oh, here. So we are basically we are summing over the final states, right? So the final states of the density that we have, we don't know what exactly it is. So that's why we are summing over it, and it basically gives me a delta function. The reason of using this is that this gives me a delta function through which I can identify the two branches that I had. And say this and this. One is going from T1 to T2, and one is coming back from T2 to T1. This minus is x bar. Taking this sum, I can get this delta function, which is at again the position coordinate at x2, which is at the final position coordinate that I have at t2. So I can identify these two branches with each other. That is basically this identification is done when you this delta function that you get can only get when you take a sum over this thing and use this fact that phi n x2 phi n star x2 prime you always have this is true for general fields, and this helps me to basically make this identification to which whatever kernel that I had here written as x2 prime, x1 prime, that I can now identify this as a simplify this, keeping in mind that in these two branches that I had, the final this x2 and x2 prime dummy indices that I introduced will always be identified with each other. So this kernel can be written in this form actually, using the delta function or this identification, which helps me understand this in a way that my contour that I will take will be of this kind. And what Sudhita is saying is, again, I think if you do the same things that you are seeing, rho nm and sum over n, again that will give rise to this kind of phi n and phi n star things. Because yeah, I'm saying that I'm performing the integration, but what I was actually not. So I have to take those elements out and write it in terms of whatever. So P and M integrated over this part of it. This sum of n is equivalent to, for example, the tracing over the x2 degrees of freedom, all possible x2 degrees of freedom along with all possible possibilities. And so if we use these three things, in fact now if we understand this minus sign as backward evolving, what we can also write is that this k is k. So this rho x1 prime x2 equals to x2 prime identification. Will actually be able to absorb all these fields into one particular contour. So basically, this was my dx kind of branch, and this was my dx prime branch. Now this branch and this branch, the final values I have identified with each other. So this whole contour now I can think of as a single Schwinger-Keldysh contour, which can be written as just dx, and this final thing again written as is Schwinger-Keldysh x prime. So this is called the Schwinger-Keldysh action, which in this case of course is sx minus sx prime, and they are decoupled. This is, say, my imaginary time contour. say this is my final finger range contour which I can get, in which we can get rid of this identification now, because I am just writing in terms of one single closed contour, time contour. The only boundary condition will be that initial times whatever value I get from this. Finally, let me just end by yeah.
So we can ask about this boundary condition also.
Yes. Yes.
So we are doing a path integral over all configurations of this X. So
Yes.
yeah. So can you explain this boundary condition once again? What does it mean to specify the initial state like this? So I'm doing some integral over X. I'm doing some integral over X over
X overall. Yeah.
So X as a functional of E. I'm doing this integral. Then what does specifying this initial state actually mean?
Probably don't have the expression
The
here.
final boundary condition that I understand.
Yeah.
Here, you are saying that when I am doing this integral, I have to ensure that the value of x2 at the x2 at the starting point is the same as the value of x2 at the turning point.
Yes. Okay. Basically, I have, let's say, when I'm saying or I'm doing this PNM calculation that I was doing, I had actually in there ANM, then some ANM star, due to which I was here my variables were x1, x2, here my variables were x1 prime, x2 prime. Now, these are basically like this, and since there is a star, there this minus sx prime was introduced. And this could be understood as this kind of thing. x1 prime, x2 prime. So if you probably the chronology of whatever I said was not very clear, but if you now identify these two parts, then what you are doing is a forward, going forward here, going backward here. So in this double system, the probability that of the initial state of the information of the initial state that you do have is at x1 comma x1 prime. So let's say this is a function of, yeah, this is not a function of anything, but let's say
That I understand.
yeah.
But I was just asking in this case a mathematical question that at the level of this integral, basically what does it mean to specify this? At the level of this integral, what does it mean to specify?
Oh, it basically means whatever I am evolving something, right? So the evolution that I am trying to make will be evolution of this density matrix or the initial state of the density matrix. I can write it in a general term, but so it will be something like rho into the power. Basically, if you have a rho, then it is equivalent to writing this to the power minus IHT to the power IHT. I am basically doing this where I am saying that at t equals to 0, I have my boundary condition as rho equals to rho 1, and I am then trying to see what is my final or the evolved things, but I am not really actually evolving it completely forward. At some point, I am coming backwards and doing this integration in terms of this closed contour. This contour is actually closed.
So is it correct to say that at the level of this integral, just as a mathematical expression, this boundary condition in itself does not mean much, but what it
yeah, at the level of this integration, it does not mean much.
use this finger tail this coordinate to compute some also.
Yes.
So then I have to specify that I'm computing this.
Whatever operator expectation value or something you are trying to compute.
Yeah. So that you have to specify what operators are here. And also I have to specify what is the initial state with respect to which I am calculating.
Yes.
And then this will become.
Yeah. There.
This.
Yeah, that is how the. For example, if you remember the PNM expression that I was writing, there also I had a K kernel. So this is the finger Keldysh kernel, where I am putting the initial condition in this way, but in general the integration will involve other operators or things like that. Yeah. So let's say let's do one simple correlation function computation. This we know is case of interaction picture. This will become 0. This is again this time ordered exponential. And now if I let's say write this row as this sum and T as the sum identity basis, then this will turn out to be and this alphas if I also, so here I expanded the operator in interaction picture. Now in this basis case, if I also make this into interaction picture, then alpha is related to the basis case and this.
I have a question. Why are you saying this dx prime integral is going opposite direction?
Because the way we are taking, since there was this ANM star, here inside this you had this was just LDT. Here you had one time direction. Here the time direction was opposite. So this, and if we use this interaction picture case here and write everything in terms of interaction picture, then basically it becomes of course at the end we will also, so here this is at the end we will take this t going to infinity, or sorry, t going to minus infinity. If you want to study something like finger Keldysh, where we start from minus infinity, go to somewhere at any time and come back. So this will be assuming t going to minus infinity, and then this can also be written in this form. If you started from the expression of rho I at some time t going to minus infinity. So the idea is that this expression, when you write in this form, again taking the interaction picture and t going to minus infinity limit, then what it basically says is that you had a density matrix, initial density matrix at minus infinity. You basically do this. I think I need to also consider another combination. You start from minus infinity. You go to some, instead of going to minus infinity, so if you absorb these two also, this will actually give you minus infinity to t. We don't go to plus infinity, but we do is we come from minus infinity to some t value. Then we insert the operator here at time t. Then we again revert back from t to minus infinity, and this will be sort of the contour that I am dealing with. This whole thing is u minus infinity to t, y inserted at t, and then coming back from t to minus infinity. Then I have my y at minus infinity. This whole phase is equivalent to what we are doing in the Schwinger-Keldysh contour in terms of the fact that we can write this as piece of some time order, not in terms of these u's, but this UC will always be involving a different kind of unitary which has already absorbed all the information of the Schwinger-Keldysh contour. That in our usual contour, this would be this. I will have to insert the y here. If I keep this outside, then this is understood as the Schwinger-Keldysh contour. This is also this most time contour defined for this. This is defined. This UC is defined in this sense, where the contour ordering, similar to, for example, we used to assume time ordering in case of usual quantum field theories. In case of the Schwinger-Keldysh formalism, instead of doing this time ordering, we will actually make this contour ordering, where we will have to take this specific contour, and this will be written in terms of this UC should be understood as in this form. So operated inserted on the upper branch of the contour first, then on the lower branch in a clockwise way, and the evolution also goes in forward time evolution, then backward time evolution and so on. Another way to do this is basically consider operators here as called as right operators, and operators in the lower branch calling them as R operators. So, for example, one easy way to see that there will be terms where time ordering is not well defined is that in a two-point Green's function, I can have this kind of operators insertions here, which will be time ordered. We can have operator insertions here in the lower branch, which will be anti-time ordered, and we can also have operators inserted in two different branches, either this case or this case. So these two will be completely no time order in such terms. When I say the contour ordering, I mean that I have to insert operators in such a way that can, where the contour will always be of this form, and I can insert operators in different places, but those operators or the Green's functions that I will compute, they will not always be time ordered. For example, they will have terms like this defined on two different branches where you cannot really define the time ordering in a very systematic way. So this is what is contour ordering. Yeah. So So we will discuss this more, and then try to discuss more clearly. Next day the conclusions are very clear, and we'll study an example which is the scalar field theory, free scalar field theory, and also discuss something which is how to, let's say, start from a quantum mechanical system and define path integral for that quantum mechanical system, and get. Also remember that whatever we have considered here, the x and x prime branches are kept independent. There is no mixed term in this Schwinger case till now. So this is just a decoupled term like thing. So what we will see that if we want to study open quantum field theory, openness, non-unitary behavior, then we will also need to involve some ISF XX term, which will at the same time have, in the same terms, it will have a coupling between x and x prime that will introduce the nonlinearity, and that term will be particularly very similar to what we had in the Lindblad master equation. That we will also see from a quantum mechanical perspective. And, this is usually this extra term is called the Feynman-Gordon influence function that we will learn about next week. Yeah, I'll try to write down the very expressions of the rho i's or the initial density matrix next day so that it becomes clearer.